Thanks to the organizers for inviting me. I'm happy to be here to talk about some novel methods to represent transport processes in ecological models. And this is, first of all, I should say I'm not an ecologist. I'm a hydrodynamic modeler. And I've worked a lot with Wim Kimmerer, who is an ecologist. He's worked a lot in the San Francisco estuary. Also a collaborator of Kenny's. So some take-home points I hope to leave you with from this presentation are that these models that I'll show that run in milliseconds allow you to do a lot of things that you couldn't do in models that were much slower. They allow for rapid exploration of alternative model formulations, optimization, and Bayesian inference. So particularly Bayesian inference, I think, is really important to quantify uncertainty, both in your parameters and your predictions, and to identify potential confounding between parameters that, indicating they can't be uniquely determined. Okay, so in order to get these really fast models, we can't do the sort of standard fully coupled model approach, so we have to introduce some approximations and simplifications. So I'll discuss those. So there are a lot of possible ecosystem modeling considerations. I'm addressing the ones in the box here, subset of the ones I've listed, but those are surely not a comprehensive list. An ecologist, I'm sure, would have many more things to add here. So I will be talking about representation of processes, what we're considering, what we're not considering, temporal and spatial resolution. And the temporal and spatial resolution, a point I'd like to make is that we don't always really need the same temporal and spatial resolution for the hydrodynamic components and the ecological components. So that's one thing I'll be talking about later. So coupling of components. So I'll be talking about some novel ways we get transport information into these other components, and how we constrain parameters, which is typically by Bayesian inference, and quantification of uncertainty the same way. Okay, so here's again a very much not comprehensive list of ecological modeling approaches, but I just want to contrast the top row with the bottom row. So some sort of obvious approaches are to use a box model. The advantage of that is it's really fast, but it essentially ignores transport in most cases. And the other extreme is to do a fully coupled hydrodynamic and ecological model where transport and transformation happen at the same time and spatial step. And that's great. That should be the most accurate approach. But it can also be slow, particularly slow if you do it all online. Can be a little faster to run the ecological part if you save the hydrodynamic results, and even faster if you do some grid aggregation or other clever approaches. But still, something that's going to run in much longer than a millisecond. So the type of models I'll be talking about are a compact model, I'm calling it, which can use some form of transport information. In other literature, this has been called, for example, connectivity matrix or movement matrix. And then I'll be talking about a more novel approach using age tracers. So this could be thought of conceptually as really similar to a Streeter-Phelps solution for dissolved oxygen. So it's basically you're moving with the water mass and it's transforming as it's transported. So let's get into those. So the first application was to longfin smelt hatching. And this was part of a larger project that Wim Kimmerer was the PI of. And Josh Corman was a statistician on this, and the other people are other hydrodynamicists and fish biologists. So very briefly, the image isn't showing up. That's too bad. I hope that doesn't happen to other. Oh, there it goes. Okay. Okay, so longfin smelt life cycle, they range from California to Alaska, and they're listed as an endangered species in the San Francisco estuary. And they live up to 2 years, and they rear in the estuary in the ocean. And as adults, they're mostly in the ocean, and they return to the estuary to spawn at age 2. They hatch in brackish and freshwater, but their eggs have never been observed in the wild, so we don't know exactly where. And what motivates this project is the entrainment losses to water diversions is unknown and thought to be potentially significant. So the water diversions have to be managed for this and other listed species. Okay, so I'm going to go through this pretty quickly. So all the details are in this paper. I encourage you all, especially if you're skeptical about anything I say, to pick up the paper. So I'll talk briefly about the hydrodynamic and particle tracking, the catch observations, the forward model, and the results. Here's our study area. Just some places I'll refer to help get you oriented here. The Sassoon Bay is, I don't see it. Sassoon Bay is here. Can you see that? No, can't see that either. Oh, laser pointer here. Okay, yeah, here. And the delta is the landward portion of the estuary. The largest flow is the Sacramento River. It's the dominant inflow. And the major exports are in the South Delta, the State Water Project and the Central Valley Project. So I sometimes think in a very oversimplified way of the delta as sort of being a conveyor belt. If organisms get into the central delta, the flow from the north is moving down to the south to the pumps and can move those organisms with it and train them into the water diversions. Okay, so the flow varies a lot interannually in San Francisco estuary. We looked at a wet and a dry year for this analysis. 2017 was wet, and 2013 was dry. And by showing the survey periods for the fish data with the X's and the O's. The O's are the annual survey, smelt larva survey, which is intended specifically to catch lungfin smelt larvae. And the ICF survey also, but the ICF survey is not every year. It's just happened a few select years. And you can see in the bottom figure that the export flows, the water diversion flows, are much higher in wet years than dry years. And that's largely to manage these losses of listed fish species. Okay, so here's the trawl data summarized for 2013 and 2017. So the catch was mostly in Sassoon Bay in 2013 and peaked around 7 millimeters in length. And then in 2017, there were also some surveys by ICF in San Pablo Bay, and that was a much wetter year. And they did find more catch in San Pablo Bay than Sassoon Bay, which is outside the range of the typical annual survey. But it also makes sense in a wet year, the adults might not get as far landward to spawn. So you'd expect hatching to be shifted seaward. So that was an important finding of previous work. And so you could ask yourself why there's such a sharp peak around 7 millimeters. Is it because there's high mortality, or is it because the larvae are transported out of the survey region by net flows? So that's one of the things we can understand with this sort of analysis. Okay, so here, just to emphasize the part that we do once and the part that we do over repeatedly, we run the hydrodynamic model once for any simulation period, and then we run particle tracking. Well, it's a lot of particles, but just one simulation. And then we gather all the movement information from that, and then we're done with that. So we don't have to do that again. Now we are going to run our forward model, the abundance model, in a statistical framework to estimate the things in the bottom box: the hatching rates, daily survival, regional abundance, and proportional entrainment. And in order to get reliable results, we choose to do that. And I mean, it's a normal choice to use 300,000 forward model runs. So we got 3 chains of 100,000 samples each for our Bayesian inference. So that's why we need a fast model. Something that runs in minutes or hours would not be fast enough to do this feasibly. And I'm doing all this on normal workstation computers, not on supercomputers. Okay, so here's our 3-dimensional hydrodynamic model domain and bathymetry, and we're showing some of the inflow locations and export locations, and there's also a lot of operable gates and temporary barriers that are put in seasonally, so it's pretty complex. We have to represent all that in the model. We've been applying this model over decades now, so we have several publications documenting our performance, and luckily we have a lot of calibration data in the San Francisco estuary for the properties we're predicting. So we've documented that in several publications. Okay, so we want to understand not just where the lungfin smelt hatch, but when. So we need to have a way of classifying each fish caught as to when it hatched. So to do that, we use otolith data. It's presented in the supplement to the paper. And from that, we can get the size at hatch, which is about 6.2 millimeters and a growth rate of 0.19 millimeters per day. So based on the length, say if they caught an 8 millimeter fish, you could trace back when it hatched. If caught on a certain day, you can trace back which cohort it would belong to. And so that's how we do that. Okay, this is the only animation I'm going to show. It's pretty basic. It's just an example of one of the groups of particles. Oh, I need to turn this pointer off, I guess. One of the groups of particles we're introducing at an hourly interval, uniform number of particles per unit area in Sassoon Bay. It's one of our regions for one of our cohorts. So we do this release over 2 weeks, and then we track where they go over the 2-week period. And you can see that this is the wet period of the year. So we're in February now. Even though this was a dry year, there are significant net outflows. So the distribution shifting seaward more than landward. But there are a few particles dispersing landward. And so this is the sort of information we use for movement. We repeat this for each 2-week period in Sassoon Bay, and then each 2-week period in each of the other regions. We use 9 regions for 2013. Okay, so going forward. So we can see here the distribution of particles at one example snapshot 2 weeks after so this is at the end of the hatching period for a different region. Now I'm shifted landward to region 6 at the confluence. We can see where those particles for a specific cohort are distributed after 2 weeks. And of course, we continue the simulation till the end. So this allows us to map the particles that hatched for any cohort in any region and to their future distribution on any subsequent day. So that's used in our regional abundance model as this lambda. It's the mapping from hatching locations to subsequent locations and times. And then the unknown things in this equation are the daily survival and essentially the number hatched in each region, which is broken up into 2 terms for the statistical modeling. Okay, so the assumptions are that larvae are passive, up to 16 millimeters, and constant in time and space, daily survival, uniform hatching within each region. The hatching rate is constant in each 14-day period, but of course varies between the periods. And the statistical assumptions are negative binomial distribution of catch and multinomial for size distribution. I mean, these are known, so these are not really assumptions, but they're part of our model. And no size selectivity of trawls. Okay, so when and where did they hatch? So here are the results. These are all presented as interquartile ranges and medians, since we did this all with Bayesian inference. So you can see most of the hatching occurred. These are in terms of number, not rate. So most of the hatching occurred in Sassoon Bay, which is this brackish region of the estuary, typically brackish, and neighboring that, and the confluence, which is 9, and the confluence, which is 6, and Carquinez Strait, which is 9, in 2013. So we can see, for example, there's relatively much less hatching in the South Delta, which would be more prone to entrainment. Okay, so we can compare 2013 and 2017, and we can see a smallish difference in timing of hatching, and a pretty big difference in distribution, where they were during the drier year, they were hatched mostly in Sassoon Bay and dominantly in San Pablo Bay in the wet year. So now that we know where and when the larvae hatched, we can estimate the entrainment in the water diversions, and this is the thing of interest to managers. This is the thing they managed to minimize this, and it was suspected it could be quite a lot higher than this, because it was suspected that there might actually be larger transport occurring than we're estimating between where they hatch and where they're actually observed in the surveys. So we actually estimated 95% confidence that the entrainment was less than about 3% in 2013 and very low in 2017, which was a high flow year. And you'd expect low entrainment because the net flows are just sweeping things out to the ocean quickly. Okay, so the conclusions, I've covered most of these, but importantly, the entrainment doesn't, although there was very little hatching in the South Delta, pretty much everything that hatched in the South Delta gets entrained. So that's where most of the entrainment losses occurred. Most of the hatching in South Delta accounted for the hatching in the South Delta accounted for most of the entrainment losses. But this amount of entrainment we estimated that definitely cannot explain 100-fold interannual variation in abundance that's observed, or the very large, also 100-fold long-term decline. Okay, and a companion paper to this, the Wim Kimmer's first author, found entrainment was low during all the years considered there, which was a much larger, it was a couple decades of data, and used a totally different approach. Okay, now even a more novel approach. This may be new to a lot of people. A part of this may be new. So this is a tracer-based approach, so no particles involved. And it's using a theory that Eric Delaire-Snyder and Eric Delis have primarily developed over the years, called constituent-oriented age and residence time theory. And we're going to use it to develop a biogeochemical model. And we're introducing, we introduced in 2019 a new aspect of that we call property exposure or property exposure tracking, which since Eric Delaire-Snyder's also written about, and we did a paper together sort of validating that approach when we had a known solution. Okay, so here's the paper. Again, I'm going to go through this one even faster, so I welcome you all to look at the paper. So some motivations, I think these will not be surprising. The San Francisco estuary has low production. It's not a highly productive estuary, partially due to clams, so food availability can be limiting to fish species. So there's a lot of interest in nutrients for that reason. Also because we have some harmful algal bloom problems. We have a lot of invasive aquatic vegetation, which may both affect nutrients and may also be limited by availability of nutrients. And the context of this is there's a really large wastewater treatment upgrade of the main source of dissolved inorganic nitrogen to the estuary, where they removed a lot of the nitrogen, but also shifted the form from ammonium to nitrate. Okay, so here are some definitions for age tracers. So the concentration is not age related. It's just if we tag water coming in from some source, say the river, with a concentration of 1, then the concentration at each point in space in the estuary is the fraction of water that came from that river. During the simulation period, of course, we don't know a starting distribution, so we just start with 0 and let it spin up to some reasonable distribution. So then we can get the age as the time, essentially the transit time from coming into the river to any subsequent time and place. So these are all 3-dimensional time-varying fields. And then we get I'd go all the way forward here because things are showing up in a strange order. Go to exposure time, which is also called partial age in the literature, and that can give you time spent in any region or time spent exposed to a certain property even. So in our case, it's time spent in the vegetated areas. And then property exposure can give you things like the average depth experienced during the transit. So the word average is important in this context. If you had a bucket of water at X1 and you could identify the age of the time since that was in the river of each water parcel or molecule, you'd find a range of age. That's in the simple form of this approach that we're using, we don't get the range, the distribution of age at any point in time and space. We get the mean time to come in from the river. So for some applications, I believe that's enough information. For others, it certainly would not be enough information. Okay, so here's a snapshot of those fields in time and also depth average, because this is a 3-dimensional model. So it's a snapshot in summer. So in summer conditions, the Sacramento River is the dominant freshwater inflow source, and we can see that sort of fills most of the estuary, except for the South Delta, where the San Joaquin River accounts for a significant amount of the water distributed in that region. And then the age, of course, is going to increase away from the Sacramento River, which is coming in on the north. So it's going to increase away from there as going to the South Delta and in the seaward direction. And the exposure time, we have some remote sensing data to tell us where the vegetation was this year, 2018, our simulation year. And that gives us, from that, we can calculate the fraction of time spent in shallow vegetated areas. Okay, and then the property tracking part, we get the mean depth experienced by the tracer Of course, this is not the depth at the location of the tracer at any point in time. That would be not interesting. But we want to know the mean depth experienced over the transit of the tracer from the river to any subsequent location. Okay, so we have a bunch of data. Yeah, luckily this estuary, we have a lot of data. Dissolved inorganic nitrogen data collected by USGS. So we had data at 8 fixed stations, and there were 2 USGS collaborators on this paper. They were the ones primarily responsible for collecting this data. And we used their high-speed mapping underway measurements of nitrate and ammonium in July. So I guess one thing to point out, I'll probably mention again, is that we had only nitrate for calibration, but both nitrate and ammonium for our validation data. And we actually do know pretty precisely what came in at the river because the wastewater treatment plant measures and reports that, and there is data just upstream of that discharge. So we can specify what came in our model. And as I said, that Sacramento River water essentially fills the whole delta, so except for part of the South Delta. Okay, so this one I'm not going to say much about. I don't know much about, so I can't say much about, but I just want to contrast this with our very simple model. So in reality, there are a lot of processes that affect nitrogen cycling, some of them biologically mediated, and some of these act in opposition of each other. So the processes that we're actually considering are these 5. So we're considering nitrification, which is conversion of ammonium to nitrate. And I should say these are all sort of nets. So there could be other processes that work in the opposite direction, and we're just getting a net transformation in our model. Okay, so we have a bed source of ammonium, a bed sink of nitrate, and then we have loss of both nitrate and ammonium in shallow vegetated areas, which could be due to direct uptake by the plants or other reasons. Okay, so here are ordinary differential equations that result from that. Pretty simple for ammonium and nitrate, but we're not going to use an ordinary differential equation integration approach. This can actually be solved with an analytical solution, so it's just an algebraic solution. And a big advantage of this approach, just like the previous one, is we only have to calculate these things where and when we have data. We don't have to calculate it on a grid or at a fixed time step. When we have a data point, we do this algebraic equation. Of course, it's extremely fast. It can be, to illustrate it to one of my co-authors actually, who was having a hard time understanding how simple it was, I put it in a spreadsheet. You can also do these calculations in a spreadsheet. They're that simple. So the things we don't know, or the things that the age tracer simulation is providing, are the age, the fraction of time spent in shallow vegetated areas, and the average depth experienced by the tracer. And the things we don't know are these parameters that we're estimating, these different rate parameters. So again, this is a bit redundant with the previous slide, but I just want to emphasize again that we run the tracer simulation once. That takes a really long time. It takes literally weeks on our PC workstation. And then we run our DIN model, which takes milliseconds. So that allows us to run this DIN model, again, tens or hundreds of thousands of times. We did this both with optimization and Bayesian inference. We found the parameters were not, for the model we landed on, to be not particularly confounded. We actually rejected some more complicated models because they did have highly confounded parameters in our Bayesian inference. But then where we landed, everything was constrained pretty well, so we ended up just reporting the optimization results. Okay, so that gives us our rate parameters and our predictions of ammonium and nitrate. So here are the rates. These are within the quite wide range of values reported in the literature. There were no values reported for uptake of nitrate and ammonium in shallow vegetated areas, but these are consistent with carbon uptake rates if converted to nitrogen that have been estimated. Okay, so the range of predictions compared to observations here. So this is showing interquartile range and 5 to 95 percentile. So mostly I want to point out that there's a strong spatial pattern that the model reproduces pretty well. And I would explain this largely by where the water has to go through shallow vegetated areas, it drops to a lower nitrate level. Okay, so for the validation, we had both ammonium and nitrate data. So again, we didn't have the ammonium data in the calibration, so this is the first time we've done any comparison to ammonium. And The observations are shown with the outer envelope and the predictions with the inner line. So you can see where there's contrast, there's some different, and where there's low contrast, they're consistent. So you can see that the nitrate's consistent almost everywhere. It's most notably not so consistent in the South Delta, where, as I mentioned, there's some San Joaquin River water that we're not tracking. And there's also a big wastewater discharge from the Stockton treatment plant that we're not accounting for. But we could, with the same method, it would just, make that simulation that took weeks with our tracers take twice as long, essentially. So we reproduced the main patterns here. And you can see, for example, a big drop-off entering the central delta near Frank's Tract, and that could be due to a large amount of vegetation in that area. Okay, so a nice thing about this really simple modeling approach also is that we can easily estimate the contribution of different terms. We can see nitrification, of course, as you'd expect, really important, but also the losses of nitrogen in shallow vegetated areas was really notable. And that's particularly worth mentioning because there's been a lot of nutrient modeling in estuary over the years. And to my knowledge, I think I know the major ones at least, no one had included a loss term in these shallow vegetated areas. So this was actually a new finding. It's something that maybe not too surprising, but no one had gotten around to actually investigating that. Okay, so yeah, again, the DIN losses in shallow vegetated areas were important. Rates consistent with other estimates. And yeah, most importantly, this is not an approach that's specific to nitrate and ammonium modeling. We've used a really similar approach for phytoplankton. With the validation I mentioned with Eric Diller-Snyder and others was for light exposure of sinking phytoplankton, and we have some sort of ongoing work with dissolved organic carbon and harmful algal blooms. Okay, so taking a big step back, the thing that these have in common are we summarize transport results in a compact form. Importantly, we only make predictions where and when we have observations. The approaches, of course, can be used to make predictions whenever and wherever, but if we're just doing some fitting of parameter values, we only need to predict where we have data. So this allows us to explore alternative model formulations, use Bayesian inference to quantify uncertainty, and some other applications that have used similar approaches that I don't think I've mentioned yet were also with Wim-Kimmerer, copepod mortality estimates, and identification, evaluation of different behaviors of zooplankton and fish. Okay, so thanks again for the invitation.